going to come. She's not going to accept the scholarship. So the next person was Rutherford. So Rutherford came from New Zealand to UK, and he studied with J.J. Thomson, right? He's working with J.J. Thomson, and then he became he graduated, and he went to another university called University of Manchester, and he started working there, right? He started working there. So influence of Thomson, he is also kind of working on atom, the structure of atom, and that is how it. So in these two universities, one of these universities, University of Cambridge, and then the other one is University of Manchester, right? There were two people, this is Thomson, J.J.T. J.J. Thomson, and this is Ernest Rutherford, right? So they were working with this. Now, he came up with this idea. But then Ernest Rutherford was not very convinced. Ernest Rutherford was not very convinced with that. So he thought, now that cannot be it. How can that happen? There is no experimental evidence for this Thomson model. No experimental evidence. Evidence for this Thomson model. So therefore he thought, okay, no, I have to kind of try and I have to really identify, give some experimental evidence so that becomes the next big thing. I told you, the science, the discovery of science is like a passion. People, it's like a fashion, right? People do something there, people keep on investigating that. And you come up with something new, and they keep on investigating on that area, and that is how science is usually developed. So, right, so this is it. There is a question now, right? So there is this question, right? Now, who had this question? Ernest Rutherford had this question. But then, let us stop the story at this point. Stop it. Stop the discovery of the atom in that point. And I want to take you to somewhere else. Right? So somebody called Henry Becquerel. He has worked with various types of radiation. Different types of radiation. His father has been working with different types of radiation. He understood that, you can use this radiation to, really understand various types of structures, right? Various types of structures. He want to investigate these X-rays, these kinds of things. X-rays has been discovered at that time. So Becquerel was using his father's steps, right? Becquerel was using his father's steps. He thought that, Becquerel thought you can take certain minerals, keep it in the sunlight for some time. So what will happen? Sun's radiation fall down, and those minerals get activated. Like our phosphor glow. I was talking about that one day. You can use this certain light to glow, the phosphorescence glow. There are certain materials, they will glow under the dark. But you have to have sunlight for certain materials. When you have sunlight, this will absorb its energy, and in the night time it gives out energy. So he was taking his father's footsteps, and he was trying to study this, understand this little better. He was working in France. In France, he wanted to work sometime, but then there was no sunlight because it's very close to winter. There was no sunlight. So he was very depressed. Henry Becquerel was depressed. He could put all these minerals into a drawer, and all the X-ray, there were films that you can develop these rays. You can detect these rays using these films. He put all these films also into the drawer, closed the drawer, and he went away. Because it is winter, there's no sunlight. After some time, the winter, that, rainy season, that part is over. He came back and he opened the drawer. When he opened the drawer, he realized that, these photographic plates are burnt. Now, why do they burn? You have to have sunlight, but inside the drawer, how can you get the sunlight? There's no sunlight inside the drawer, but then these photographic plates are burned. I was wondering why this is, what is going on here. Couldn't understand that. He tried to understand it little better, and he discovered a concept called radioactivity. Radioactivity. Active compounds. So, who discovered radioactivity? Henry Becquerel discovered radioactivity, radioactive compounds. Right? So, there we will put a photo here. Like, this is Henry Becquerel. Right? So, he is the one who discovered radioactivity. Now, this is without sunlight, there are certain minerals itself can give out energy. And then there's some kind of a radiation emitted out. So why? Because unstable isotopes, they try to become stable. They try to stabilize. That is why this radiation is emitted. Now there are even back in the days, people never realized this. There were certain there was some glassware also that can give rise to this kind of a glow. Can you see a glassware? There's like a wine glass kind of a thing, which is giving a glow, right? So this glow is given by this material. He didn't realize. He realized that this is something new, and he found this new method, which is called radioactive. Now you all know this famous scientist Marie Curie. She looked at these radioactive materials better, right? She is the one who looked at these radioactive materials better, and then she discovered even more things. She discovered polonium, radium, polonium, thorium. These new materials were discovered, new elements. Were discovered. Huh? Right. Now, this is a famous photograph, taken by, this is Professor Curie's hand, this photograph is called. Like, you can see a burning patch. Like, Professor Curie, Marie Curie's husband, has put a radioactive material on the arm, and it has inflicted a very bad wound. Right? Very bad wound. And then this is thorium, not TH, thorium. Very bad wound which will never heal. They discovered a lot of things. Then they understood that there is some new material which is called radium. So, right, radium and thorium isotopes. These are there. Now, these thorium and radium isotopes, they emit three types of materials. One is called the alpha particles. Alpha particles. Then there is something called beta particles. Beta. And then there is something called gamma radiation. I'm sure you have heard that. Right? Alpha, beta, gamma radiation. Right? Alpha particles, They are like, really massive particles. They can emit, alpha particles are massive particles that can emit like this, right? Let me remove that and then put it again somewhere here so that you all can read it properly. So that is alpha particles. These are alpha particles, right? Alpha particles are like they later understood that there are two protons inside this, two protons, and then two neutrons in it. Two neutrons in it. So this entire set of particles combined together, we call it an alpha particle. Alpha particles. Alpha. Because protons are positive charge, this has a +2 charge. Charge is +2. Charge is +2. Right? Now let us say you have a element. Let us say you have an element A. Element A. Now up here you write the mass. It's called the mass number. You write the mass here. Down here you write the charge. Charge in the sense the number of protons. Number of protons. Right? So if you have, let us say, some element A here, let us say 25 and 13, something like that. Right? When you emit an alpha particle, alpha, you give a symbol alpha like that. It's a Greek letters, first letter, alpha. Alpha is 4 and 2 plus. Then, let us say you turn this into a new element B. Right? So, out of 25, 4 is deducted. So, what is the remaining number? Out of 25, 4 is deducted. What is the remaining number? 25 minus 4, you get 20, what? 21. Right? So 21 plus 4, these two should add up to this one, 25. Right? Now here it is 13, here it is plus 2. What would be the number down there? Number of protons there. Can you all tell me? What is the number of protons? If there is 13 here, 2 here, what is the number of protons? What would be the number of protons? 13 minus 2. Right? Very, very primitive arithmetic. What is the number? So you get, what do you get? You get 11, right? So 13, 12. Let us say you have P here, 43, let's say 20. What do you get? If you emit an alpha, it will give you 4, 2 plus. What is the other material that you would get? Let's say this is Q. Can you tell me the numbers? Q, what is the number? 43, 4. What is the number? 43, 4, 39, isn't it? 22, that will be 18. So likewise, it emits this alpha particle which is positively charged. So that is what is meant by an alpha particle. Alpha particles are like that. Then they realize there's something called beta particles. Beta particles. Now let me show you beta particles. Beta particles are fast moving, very tiny particles their mass is very small, right? So therefore we say 0, this is -1. Charge is -1. So here the charge is -1, like an electron, mass is very small. Mass is very small. So they realize that if you have, let us say A, let's say 50 and 25, if you emit a beta particle, what do you get? 0 minus 1, what do you get? What is the other one? Let us say you get C, some element C. What are the numbers? 50, this is 0, that means 50. That means top parts you should balance 50, 50. 25 minus 1, that means 26. So this is the new element that you get. It's a new element that you get. Think about another example. Let us say you have a new element. Let us say element symbol is U, and this has 75 and 38. And if you emit the beta particle, what do you get? 0 minus 1. What is the other? Let us say T, new element. These are not the real symbols. These are different symbols, right? So 75, 0, 75 it should be, the upper part. 38 minus 1 is equal to, what is that? 39. So that is the new element that you get. Likewise, beta is a fast moving, like an electron. It's actually a fast moving electron. So that is called a beta particle. Now, if you look at a gamma particle, the other one is, it's not a gamma particle, we call it gamma radiation. So how does it work? That gamma radiation, how does it work? So gamma radiation work based on this, right? Gamma radiation work like this. Now let me put that there. So we can look at gamma radiation is like this. Now it is a type of energy, like the X-rays, like the light. It's a type of energy. So it doesn't have a weight, doesn't have a charge. So let us say you have a new element. Let us say 100 and this is 50. And this is still 100 and this is 50, but emitting gamma radiation 0, 0. This has high energy. The high energy is gone down. That's the only thing, right? It's like before dancing and after dancing in a party, right? Before dancing, people have a lot of high energy, but then after dancing, they are knackered, right? So that is it. So this one has a high energy, yeah. And this will have low energy. So that excess energy is given out. So they realize this. Actually, like, these things were discovered by Henry Becquerel. And it was experimented by Marie Curie and Pierre Curie. And they discovered a lot of elements. And there were 3 particles that they discovered. They discovered the first particles to be alpha particles, having a +2 charge. Then they discovered these beta particles having a -1 charge. They discovered gamma radiation, which is not a particle really, beta, gamma particles are emitted. If you have a radioactive material, it's unstable. Radioactive material, this radioactive material is unstable. So it emits this alpha particles. Alpha particles are emitted. So what is that? 4 plus 2 emitted. This emits the beta particles also. Right? Emits the beta particles. Minus 1. And it also emits this gamma radiation. Gamma radiation is emitted 0, 0. So 3 things that are emitted out of this. So by doing that, it stabilizes. This guy gets stabilized. So let us say this particle that is there, it gets stabilized. So you see that the particle get stabilized. So this is stabilized. And these radiation are, you have the particles. Now, what are the 3 particles? Alpha, beta, gamma. They are named according to the alphabetical order. Alpha is the heaviest particle. Then comes the beta particles. Gamma radiation is not heavy at all. So that is how they are emitted. So 3 different particles. So what is radioactivity? Radioactivity is a naturally unstable isotopes by emitting alpha particles, by emitting beta particles, gamma radiation, they try to become stabilized. So that is why even inside the drawer, they start emitting it. And these particles are really bad particles. And radiation, gamma radiation, alpha particles, beta particles, they are very bad ones. They are like highly ionizing. They can cause cancers. Now, but then gamma is also used to treat cancers as well. You can treat cancers also, but then they can cause cancers as well. Right? They can very easily break bonds and make new bonds and do all kinds of malformations there. They didn't know at that time. That is why, Marie Curie died prematurely, with cancer. They were exposed to cancer at that time. They didn't know any of these things. The funny story is at that time, this gives a nice glow, right? They realized that this gives a nice glow. This is this one, right? It gives a very nice glow here, right? You see the glow. Yeah. So because of this glow, people realize that, even inside the darkness, you can see them. So people painted pictures using radium. They didn't know that this is radioactive. They take these fine paint brushes, dip it in radium, and then they paint. Now, especially girls. There were so many girls painting these pictures in one room. And then when they want to make the paintbrush really thin, they actually put it in their mouth, it seems. Put it in their mouth and then made it very fine just to get these very thin lines. All these girls, they got cancer. They're called radium girls. Radium girls. They didn't know. They never knew that this is it. So this self-inflicting wound, right? Professor Curie was carrying a radioactive sample in his pocket, and then it has touched his skin and it has inflicted the wound, and he tried to cure it for a long time, it seems, but couldn't cure it for a long time. Not any of those antibiotics answered, it seems, at that time. So likewise, you see that there's this new discovery took place while Ernest Rutherford is in UK, right? So these things took place in France. So this took place, right? And then one day, this is what you have, right? And then we need to understand their properties also. Now, properties. If you look at the Alpha radiation can't penetrate much, right? So let us say you have, okay, I might have a small diagram for you, right? Okay. So let me put the cursor there. Otherwise, it will be very difficult. Right. So there we will look at this. So this is what how the penetration is. Alpha particles can't penetrate much. So as soon as it goes on to this, like even a tissue paper, it will be blocked. Alpha particles are blocked because they are massive particles. Massive particles get itself blocked. But beta particles are not like that. They are tiny particles. They can go through but the tissue paper, but it will be blocked by aluminium. If you have aluminium. Now gamma radiation is not like that. It's radiation. So it will go through the paper, it will go through aluminium, but can be blocked by lead. That is why, you use lead when you're doing X-ray, X-rays. When you take an X-ray, they put a lead coat around you just to block it. Radioactive waste is stored in a lead container. All these, India, Japanese, Japan, and all that, all of these places, Russia, all these radioactive waste is stored inside lead containers, so that it is not going to expose outside. So that is that. So these are gamma has the highest penetration power, right? So that is it. Penetration is really high for gamma, right? Alpha particles have the lowest penetration power. So if you want to control the thickness of a paper, you can't use beta. How thick the paper is, it will go through paper. So you use alpha particles. Alpha particles are the best. If it is really, really thin, alpha particles can go through. But if it becomes slightly thicker, alpha particles can't do. For example, about 65 GSM, 70 GSM, 80 GSM. There are kind of various ways of measuring the thickness. So that is that. Using that kind of a thing. So you use those kinds of techniques are there. But let us look at the ionization power also. Ionization power. The highest ionization power is for alpha. Alpha has the highest ionization power. O2+. Right? Highest ionization power. Highest ionization power is for alpha. Right? Now beta has a lower ionization power. Gamma has an even lower. It has a ionization power, but it has a very, very low ionization power. It all depends on the charge. Higher the charge, higher the ionization. Lower the charge, lower the ionization. Ionization means separating charges, separating people. Like the racism. If you are a racist, you can separate people. But if your racism is low, then how you interact with others might not lead to racism, might lead to harmony rather than separation. So like that, if you have a very high charge here, you see a high charge here. Here you see a high charge, +2 high charge, so highest separation. This one is a slightly a lower charge, so lower separation. And this one has no charge, very, very tiny amount of separation. Very, very tiny. Because of the radiation, when it is traveling, some of these things can collide and separate also. So because of that reason. So ionization power is highest for alpha particles, lowest for gamma particles. Now let us look at the velocities of these particles. Velocities. Velocities. Right. So velocity depends on how fast the particles can run. Imagine it like that. Very easy. Like, bigger, like a person, like a Zumo, like a thin person like Hussein Bolt. And imagine yourself there. Right? A person like Zumo, 100-meter race might be difficult for him. He might be good at wrestling, but then for 100-meter race, Zumo it might be difficult for him because he has a bigger weight and it's very difficult to carry that weight for a longer time. So if the particle is larger, so this is the alpha particles, O and 2, it is slower. Then comes the next particle, the smaller particle, which is the beta particle. So you see the moderate speed. And then gamma radiation, now no weight, it has the speed of light. That is why in the electromagnetic radiation you have gamma, but you don't have alpha and beta. So speed of light. It looks like a EMR, electromagnetic radiation. So that is how you get this. So bigger the particle, slower it is. That's a really important highlighting factor, right? So I will highlight that as well. Huh? Slow it is. You can straight away take that note as a note. Huh? So that is like kind of a really important thing. So these properties were understood none other than Ernest Rutherford. Actually, Ernest Rutherford, I told you now, we stop the story at this point, remember? So he was in University of Manchester, right? And then, he was worried like there's no experimental evidence for this. But then, he has better things to worry about. He also had that problem, but then he was working, Rutherford, like the modern day Elon Musk, his laboratory produced so many Nobel Prizes, right? These are like bullet people back in the days. So he was like thinking about a lot of things. And then, so in a conference, he went to France and he met Marie Curie. Marie Curie is a Polish lady who has come to France to do research. So he met now like Marie Curie is like, Madame Marie Curie at that time. She's like very popular. And then Ernest Rutherford met her, and then actually she gave a polonium isotope to Ernest Rutherford. So gave a polonium isotope, a radioactive material, to our friend Ernest Rutherford. And he took this to England. Now, actually, there's always a saying, if there's something good, Sri Lankans are always there. So, in that era, the British were ruling Sri Lanka. And then there's this place called Nellore in the southern part. there are radioactive materials in Nellore. And they have taken some samples from Nellore, and it is reported that actually Rutherford was given these samples, right? Radioactive material from Nellore, right? I had a small article, and then there was this, one word saying radioactive sample from Ceylon was taken, right? So I read that very recently. Also, I read that, and even back in the days, I have heard that. So it was, anyway, it was given, if there is something successful, we are always there to help them and all that, at least even though we don't help, we say that, every success story has so many fathers. So, so Ceylon, we were there, right? So we were taking, we have given them this radioactive material, it seems. But anyway, so Rutherford has access to this polonium isotope. Now imagine this scenario, right? Now Rutherford is a very popular man, very popular man. Why? Because at that time, he's running a new thing, so many different discoveries. He has named alpha, beta, gamma, all these radioactive materials, all that. So very popular man. Hmm? Popular man. Then there was this somebody called Geiger. Giger, I think. Giger, Geiger. Geiger Muller. Right. Now, some of you might have watched these movies, maybe these episodes that they're called TV series, right? Yeah, TV series. What are these two TV series? One is called Chernobyl. You might have watched this. I don't know. I don't know what you guys watch. You don't even talk to me. So I don't know what you watch. But then, uh, yeah, the kids that I know, they are well into these kinds of things. I don't know whether we have geeks here. You guys are the cooler guys, no? Right? At least pretend to be cool, right? So these people watched, they have watched, 1 year back, there was this story called Chernobyl. Chernobyl, there is another one, you might have it in Netflix also. There's this, yeah, Fukushima disaster. Fukushima disaster. There's a kind of a documentary. I think it's like a documentary thing, documentary series where they talk about Fukushima disaster. I can't remember actually what days. I think it's called Days. So 7 days or something like that. In 2011, there was a disaster. There's a tsunami struck, and then how the nuclear waste plant was destroyed, and then how this nuclear waste was given out. They always talk about Geiger Muller counter, Geiger Muller counter. Geiger Muller counter is a counter. Yeah, this is a small device where you take that device and it will tell you how much of radiation you are exposed to. So this is that same guy, Geiger, who made this device. Even we use it nowadays. So that great guys, huh? Imagine working with brilliant people. Rutherford is so many ideas. It's this Geiger, right? So everybody wants to work with him, right? Everybody, like even in your university, might have these small dreams. That you have a kind of a lecturer who you like to work with, right? But then, bring all those lecturers together, all these popular lecturers together, you will get Rutherford. It's like that. He's a big character, very big character, Rutherford, and then his postdoc was Geiger. And imagine, there are so many people working, so many Nobel Prizes, so many people working with them. So there is this young undergraduate, just like you guys, right? First year undergraduate. His name was Marsden. His name is called, he's called Marsden. Let me see whether there are any pictures of these people. Yeah, there you have it. This is our friend, the big guy, Rutherford. Huh? Right. Right. This is the Geiger. This is Geiger. This is the young guy, Master. Right? That is it. So these are the three people now. I think it is like, after several years. Rutherford, Geiger, and Marsden. So this Marsden comes in, like, one day, he, like, no email and all that, right? He comes and he says that I want to work for it. But Rutherford is like now, like, popular guy and a very popular big shot. He didn't know several people who like to work for him. He didn't care for this, like, lousy undergraduate. He said, come again some other time. But then this Marsden like guy, you know how this young energy works, right? Young energy, you never give up. So the thing, the young energy is that you never give up. This guy, he appears in the next day also in front of Rutherford's house, like not the house, like, in his laboratory, in his office. Rutherford, I want to work. Right? But then he didn't take a good look at him. Like, who is this guy? All that. But then he is like, persisting, insisting, and then, like, every day, he, like, just before the sun comes out, he is there. This guy is there, Master. All there. Then, he got, like, really, really pissed off with this guy who, Marsden, this young, lousy undergraduate. He thought, I'll give him a nice job. And he asked him to do some kind of experiment with the help of Geiger. Now, undergraduates are never supposed to do on their work on their own. So there's always someone to help you. So we thought, okay, let us do a nice experiment. Let us do this nice experiment. What you do is, you keep your radioactive material in a small case, like this. This is made out of lead. Why lead? Because it won't penetrate. It's lead, right? It won't penetrate. So keep it inside lead. This is your radioactive material. What is that? Polonium isotope. Polonium isotope is an alpha emitter. What is alpha emitter? It emits alpha particles. It keeps on emitting alpha particles. Every now and then, it emits an alpha particle. Right? So if you keep a Geiger counter here, right? Just keep a Geiger count on this side, right? Somewhere there on that other corner, it gives a beep. So if you keep a Geiger counter in front of a radioactive material, it gives you beep, 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 beep. Likewise, it gives you beeps, several beeps. So you can count the number of beeps and you can see how much of radioactivity is there, right? By the way, watch this. What is this? Chernobyl thing. So you will see this Geiger count, all that, they're there. It's a good TV series to watch. Like, kind of, right? So, and then he thought, okay, make a very thin gold foil, right? And then count the number of particles that are emitting. Right? This is keeping 180-degree angle to this. Straight away, 180-degree angle. The Marsden was very happy to do this. He just went there and did it and he counted and all that. Come back next day morning, just to annoy Rutherford. You've done it. You've finished this. Right. Then do something else. Right. Change this angle, right, in that direction. Change this angle in that direction, right, up to this point. Change this angle in this direction, this point, in maybe 30-degree angles and see and get a count. Actually, he didn't expect anything to observe. Right? Rutherford didn't. It seems that Rutherford didn't observe anything to observe. He didn't expect anything to observe, anything peculiar to observe. He just wanted to get rid of Marsden, it seems. Because they're like, this guy is always persistent and every day he's there in front of your room. And he got annoyed. Said, okay, I'll give you something that it will take some time to do. But you know about our Marsden fellow. Marsden fellow is also like, very energetic and he want to do this. And he has done it like, immediately, like, few days, few nights and few days, few weeks. He is again appearing again. Like, comes and, he says, this is how the scattering look like. This is how the scattering look like. All that, he come and explain. Now, Rutherford thought, this guy is like a kind of a good guy. He knows his stuff. And then he asked him to do this, like, changing 1 degree at a time. Like, so it will take a lot of time. But then Marsden was at it. He took this Geiger counter, keep it 1 degree at a time, and he counted all that. He came up with this very nice spectrum out of it, and he showed. Now Rutherford was curious, like, this can't be it. He thought if a radioactive particle travels in this way, like, these are very thin particles, very thin gold foils, right? Thin gold foil, this alpha particle will penetrate through and it goes on to this side. But it is not like that. He said, like, he realized that if you record 8,000 beeps here, right? 8,000 beeps here, 1 in 8,000, it goes on to that side and, it gives a scatter there. I will count. 1 in 8,000, it goes on to that. So small angles, 1 in 8,000, it changes its direction in small angles. So he realized 1 in 8,000 changes the direction in small angles. And also he realized that, 1 in 25,000 changes the direction in large angles. Right? 1 in 25,000. That means if you record 25,000 beeps on the other side, one of these will completely scatter back in the opposite direction. Right? So changes the direction in large angles. Changes the direction in large angles. Right? And then they were able to look at this 1 in 100,000. Right? That is 10,000, right? 100,000 completely have 180-degree change. So that means it goes in that pathway, it comes back in the same path. This was astonishing. Like, this is a tissue paper now, right? Tissue paper. And alpha particles are massive particles. Realize that, it goes into this. But then some of these particles, scatter back. Like, he actually explained this, Rutherford explained this. It is like you are hitting with a bullet. Like, take a tissue paper, hitting with a bullet. It hits on the tissue paper and scatter back and come and hit on you. It's like that. The explanation that he gave it's like that. Rutherford thought there's something great about this. And he wanted to do this experiment better. And then what he did was, he did this experiment. Yeah. So this is what he saw. He realized, you see this alpha source, right? Let me show you that. Alpha source is there. Yeah. This is your alpha source. This is the polonium isotope. This is this polonium isotope there, right? And alpha particles are penetrated in. So he used this collimator to kind of make a narrow beam. And when they start hitting, you can see, like, it hits on the gold foil, and you can see that, like, a lot of particles hit there. Lot of particles hit there. But you can see 1 in 25,000 hits somewhere here, and the other ones you will see hitting somewhere there. So this is something great, and this is called the Rutherford's gold foil experiment. Why do you call it Rutherford's gold foil experiment? Because Rutherford is the one who did it, and he used the gold foil. He actually used 12 different elements. 12 different elements. The best results were given by the gold foil. That is what he reported at the end. That is why it is popularly called Rutherford's gold foil experiment. Also called alpha scattering experiment. Alpha scattering. Also called alpha scattering experiment. Now, because of this reason. Now, he couldn't explain it. Now, this one he couldn't explain. He was wondering, how come? How come you see this kind of a effect? Like, he thought if the matter is neutral, according to the Thomson's plum pudding theory, where you have the plus here. Now, remember, Thomson is his teacher. Like, electrons are there. Right? So matter is completely neutral now. So he thought, alpha particles will move from here to there without much of a deflection. Maybe minor deflection might be there. Right, let me change the color. Minor deflections might be there. But then most of these alpha particles should go through it. Might happen. Most must penetrate. But that didn't happen. That didn't happen. So based on this, he said that this structure of the atom is wrong. He said that, like, he actually calculated, not just speculations. His paper is like kind of really long. There are a lot of mathematics in it. We will get rid of that mathematics. We'll get rid of all those ideas. But then I will look at the conclusion. Conclusion, he says, right, the matter is composed of tiny particle, which is called the nucleus. And the radius is roughly around 10 to the power minus 13 centimeters. Right? The next one is the atom. The atom is like, really big. Atom is like really big. Let me draw that. Right? Atom is like really big. It's like you put a marble in the cricket field, one marble, and if you look at the entire field, it's like the atom. So this is the nucleus. Tiny little space is called nucleus. And the radius of the atom is about 10 to the power minus 8 centimeters. So he said that this entire mass of the atom is concentrated into a tiny space called a nucleus. And that is positively charged. Positively charged nucleus. Charged nucleus. And the atom is really large. Right? So that is what he said. Okay, so there you have the structure of the atom. So this is called the nuclear model of the atom. This is called the nuclear model of the atom. So, right, so let me do that properly. Nuclear model of that. Right. So Rutherford proposed this nuclear model of the atom. Right. Okay, maybe there we will stop today, and then next time when we meet, we will try to understand a little bit more about this thing. So I will send this document to your doctor, like who is in charge in this course, and then you might be able to get it from her. Okay? Right. Then, okay, thank you very much. Thank you for joining, and have a good holiday. Right. Thank you. Thank you very much. So I will stop this meeting. Thank you.